All right. Hello, everyone. Welcome to today's Corundum developer meeting. Thanks for taking the time to tune in today. All right. So primarily today, I have just a few status updates over what I've been working on over the past couple of weeks. So let's go ahead and get into it. All right. So um, let's see. There's the PCI Express related bug that I uncovered that I've been chipping away at. There's still a bit more implementation to go before I can, tell whether that's been fixed or not. But making progress. I've also started working on some of the DRAM integration stuff. That's kind of been on the roadmap slash to-do list for a while, but I'm taking some time now to bring that up on most of the Xilinx boards and put in a lot of the infrastructure so you can actually use the DRAM from inside the application section. Um, and then the batch completion write support is basically on hold until I fix the PCIe IP core related issue because that seems to be triggering it. And the rest of this is all kind of carryover stuff from before. So once I get the batch completion right, then I'm going to turn the crank on variable length script support, and then yeah, management software 10G25 D-switching and some other informational stuff is on the to-do list. All right, so let's take a look at these one by one here. So the PCI Express bug that I bumped into before, basically, it seems like there's some sort of issue in the internal tag management or internal buffer space management logic in the UltraScale Plus PCI Express hard IP core. And under the right conditions, it seems to be losing track of the buffer space. And it drops a bunch of operations, and then the whole card hangs because those operations never complete from the standpoint of the rest of the logic on the FPGA. In general, the core or the part IP core should be doing things like keeping track of timeouts and reporting when an operation timed out. But that's not taking place here, so there's no indication one way or the other that the operation completes, and the rest of the setup hangs. So not so great. What I've done so far on this is implemented the tag management in the hard IP core model, in the Coco TBX to PCIe model. I have not cut a release yet. I'm going to wait on doing that until I have basically verified that all of my assumptions and whatnot are correct about how that actually works. Once I do that, then yeah, I'll go ahead and push that up and cut a new release and whatnot. What I need to do next is to update the DMA engine to utilize this functionality, and I'm working on that now. So hopefully that won't take too much longer, and then I'll put all the pieces together and we'll see what happens. Hopefully it fixes a bug, because the idea is we won't send TLPs to the hard IP core if it doesn't indicate that there are some tags available. So I think that should probably work out nicely, because it seems like what's going on now is we're basically giving the core more packets than it can handle. And I suspect there's some sort of a back pressure related issue where it's accepting something but it shouldn't, and then everything gets screwed up. So if we don't give the core packet to begin with, then hopefully there won't be a problem. All right, so that's that. I was working on that last week, or I guess 2 weeks ago. Last week, mainly what I was working on is the DRAM integration. So the idea behind this has been kind of on the roadmap for a while, in terms of the future of Corundum is taking any on-card memory, be it HBM, DRAM, whatever, and connecting that up in a way that the application section and the core data path can access it. So the first component of this is to bring up all of the memory controllers and memory interfaces on the FPGA, and provide basically AXI connections that go all the way down to the application section. So I've gone ahead and modified the code to add AXI pass-throughs into the core application logic, or from the core top-level files all the way down into the application logic. And for most of the UltraScale Plus targets, I've gone ahead and added the appropriate DDR4 MIGs and HBM controllers and connected everything up. And the only testing that I've done so far is to see that the calibration completes the Xilinx devices very nicely report this via the debug hub if you plug in the JTAG cable. So that makes it very easy to check that the MIGs and HBM controllers at least have all their clocks and reset and I/O connected, and that they're completing their internal calibration and initialization steps. So I've not tried poking at them over the AXI interface to see if everything is hooked up correctly there, but this at least makes sure that all of the correct pins are wired up at the board level. Let's see. So the next step, well, so a couple things are on the to-do list related to this. So Intel devices also have a similar kind of soft memory controller, but they have the Avalon memory map interface. So for the Intel devices, that's going to have to be adapted to AXI. Haven't looked into that yet. Hopefully that's not too bad. The Intel HBM controllers act a bit differently from the Xilinx ones in terms of how they handle bursts and AXI IDs and a couple of other things. So I need to take a deeper look into that. They also don't have provisions for switching across all the ports. I think they have some sort of a soft switch option across groups of 4 ports, but they don't have like a unified address space across all the ports, which is potentially useful if we're going to connect up the memory controllers to the internal DMA engine and to the PCI Express bar. It would make sense, instead of connecting to all 32 ports separately, if we could just connect to one port. Obviously, you might not get quite the full bandwidth, but it certainly simplifies things on the logic side. So we might need to add some sort of switching setup. Full crossbar is probably not such a good idea from a logic resource perspective. On the Xilinx devices, they seem to use these, I mean, I think it's implemented in hard logic, but they have kind of these 4-port with sideways traffic blocks that sit on, groups of 4 ports. And it's set up in such a way that that any port can access any port, although not necessarily with the full bandwidth. So at some point, it might make sense to look into trying to implement something similar that it could drop onto the Intel FPGAs for kind of similar cross-connect capability, but without a stupid amount of logic resource utilization. And also to deal with the differences in how AXI bursts are supported on those. And then I also need to bring up MIGs on 7 series devices, which we can circle back to that later. Let's see. And then the long-term to-do is all of the integration into the Corundum core logic. So right now it's just the AXI just goes all the way straight through the application section. It doesn't connect to anything else. But the long-term to-do is to provide options for connecting it up to a separate PCI Express bar. So right now we have bar 0 for the main control components. We have bar 2 dedicated for the application logic. So the idea is that bar 4 could be connected up to the memory subsystem. So all of the DRAM, all of the HBM, whatever controllers are present, those will be accessible through bar 4. And then that will support both software accessing stuff as well as things like peer-to-peer DMA. So if you wanted to have 2 cards talk to each other, you'd be able to do that. Let's see. And then the last piece is to connect it up to the DMA subsystem. And this means that if you're using the DMA engine to transfer data, then it doesn't matter if it's coming from host memory or from card memory. The DMA subsystem will figure it out effectively by comparing the address against the bar configuration and saying, oh, this region corresponds to DRAM versus host memory. So this will mean you can do fun stuff like allocating memory that corresponds to on-card memory and sticking it in descriptors for receiving packets and sending packets and things like that. And everything should just work. But it's going to require a few more odds and ends to get to the point where that's doing what it's supposed to do. So that's kind of the status in terms of the DRAM integration. There's progress being made, but there's these couple longer term to-do items that we'll have to circle back to a little bit down the road. All right, and then that brings me to the batch completion write support that I was working on previously, and right now, it's showing signs of life. Things definitely are doing what they're supposed to do. Some optimizations are going to be needed to reduce resource consumption and potentially to improve the timing. But right now, this is on hold until I have the PCI Express bug fixed in terms of that, in terms of the tag management. So once we get that sorted out, then hopefully I'll be able to get this an earlier version of this committed and integrated into the at least my development copy. Once we have that a little bit more fine-tuned, then and probably also get the rest of the variable length descriptor support, then we'll go ahead and push that up into the main repository. All right. Anything else new here? Let's see. So didn't remove the graphs from before. If anybody wants to take a look at those again, there's nothing new here. So I haven't done any work on this since last week. Right. Okay. Variable length descriptor support, that'll be up next. Same kind of idea in terms of improving the throughput and the utilization over PCI Express, but yeah, this one blocked on the completion right support that's that I'm getting finished up. And I think that's about it. Everything else on here is kind of some more details on that. And then everything else kind of carry over to do in terms of management software, 10G25P switching, and the clock info register block. So that brings me to the to-do list. I guess one other thing that I should mention real quick is I've been taking another brief look at the checksum offloading support. Tao Wong was asking me a couple questions about that because he's doing some stuff with TCP, and I was taking a look at the Linux kernel support for checksumming packets, both on TX and on RX, because I have a couple different options for that. And the software guys really like it when the hardware does things in a flexible way. So the simpler offloading that I implemented in Corundum previously seems to be the one that the software guys prefer, as opposed to what other NICs do, which will fill in more details without software having to do much work, but it's only works for certain types of packets. But the flip side, if you're generating TCP, IP, UDP packets on the FPGA, it would make sense to have some sort of way of inserting checksums in an automated fashion. So with that in mind, in terms of what the Linux kernel is expecting for checksum offloading in a more protocol agnostic way, what I'm thinking might make more sense for the checksum offloading on the NIC is to perhaps have a module where if we have a if we're generating packets on the FPGA, we can basically generate the checksum command for the existing checksum offloading component, and I guess potentially also deal with the IP header checksum in addition to that. So instead of having to rewrite the entire checksum offload components, just kind of augment the existing one. So haven't totally finalized that, but that's kind of what I'm thinking about there. Anyway, that about rounds it out for the status updates for now. If anybody has any questions or comments, go ahead and fire away. Or if anyone has anything that they would like to discuss, I'll go ahead and open it up.
What did you think was the date on getting the DRAM into the tree?
I'm going to try to get that done this week. I was actually, my goal was to get that kind of initial version of it in there by this weekend, but a bunch of stuff came up this weekend. I was super busy, so it'll probably take a couple of days, but yeah, that should be operational this week.
All right, I'll sign up to beta test.
Okay, nice. And I also have it working on the SOC 250 already, so the MIGs are operational.
Yeah, perfect. That was on my list to do for sometime in the next month. So
right, yeah, that'll definitely be a time saver for a few people, I think. The other thing that I'll note that was kind of interesting is that it seems like a lot of boards list their DRAM support as 2400, but apparently UltraScale Plus supports 2666. for component memory, when it's not in a DIM. So for all the boards that had components on there, I said, okay, well, let's see if we can get it running at 2666. So I think most of them I was able to do that with only a couple of exceptions. I think the Exynic X100 board, for whatever reason, I was getting a failure on the complex pattern test during the calibration. So I had to drop that one down to a little bit more than 2400.
Okay.
But the SOC 250 runs at 2666, it seems. So I guess we'll have to see. If we're running into weird issues, we can drop that down at just a couple lines at TCL to change that.
Yeah,
But yeah.
all the standalone stuff has run fine at 2666.
Okay. Oh, so you've run the 250 SoC at 2666 or?
Yeah.
Okay. Well, that should be fine then. Cool. All right. Does anybody else have any questions or comments, or are we going to turn it over to MLE, who I'm sure has a lot of stuff to ask about as usual? Trying to give an opportunity for anybody else that might want to add anything. Going once, going twice. Apparently not. All right. Well, I guess Ulrich and Joachim, go ahead, and if you have any questions, fire away.
Okay. Yeah. So I guess we at this point we can continue the private chat discussion.
All right.
So perhaps for the others, we're working on a custom board, Intel-based board, and experiencing performance issues, which means in this case, yeah, packets being dropped, especially in case of TCP traffic. And well, we are debugging ourselves through, yeah, the path to the problem, I would say. And the last thing was that we see that queue manager, to be specific, the descriptor fetching mechanism returns errors in exactly the amount of packets which are lost, or which we think are lost according to other counters. And we were wondering what error means in terms of descriptor fetching. And Alex, you said that it's indeed just a queue being disabled or inactive.
Right. Yeah. So I took a look at the code. It reports two different status bits. There's the error status bit and there is the empty status bit. So you get the empty bit if it tried to dequeue from the queue, the queue was active, but there was nothing in it. So it was empty. If the queue was not active, then you get the error status.
Yeah.
And as far as I can tell, that's the only way that status can be generated. Right now, it's not even looking at the DMA. So the DMA engine does report status, but that has not been properly connected up to everything yet. So if the DMA operation fails, it proceeds as if the DMA operation succeeded, which is not great, but we can circle back to that later and do something better. But yeah, so the only thing that should result is in that in an error is trying to send on a queue that has not been activated. So my thought right now is that maybe you didn't activate all of the receive queues, and for some reason a packet is being sent to one of the queues that wasn't activated. But I'm not sure I'm not sure how you have it set up exactly.
Yeah, unfortunately not. All queues should be enabled and are enabled according to mqnix dump, for example. In this special test case or kind of basic test case, we are not even using our special driver add-on in any way. So we have all queues enabled, kind of the
This,
in the
this is just
default
basically
mode.
with the default driver. Yeah.
Yeah, and so yeah, this would mean from my point of view now, either some piece of software is writing to the activate bit of the queues, or especially of the one queue. I mean, we are doing TCP traffic here, so RSS has no chance to choose other queues. It's always should be the same queue for the same TCP stream. So either software is toggling the active bit, but the question is which software. The driver shouldn't do that. I mean, it's if config up, test, and down at the end.
Well, so one thing that you could try, do you have enough logic resources available to put like an ILA or whatever the Intel equivalent is, a signal tap on there? Not really.
It depends. We have to check that. For now, we are working with adding counters.
Right. Well, so what I was going to say is that if you could just monitor the just that status interface on there, trigger on the error bit getting set, and then look at the queue index and just see, are we seeing like 10 operations on the same queue and then one random one in the middle just fails for some reason? Or if there's something else weird going on. It's like, I don't know if a counter would necessarily tell you that, but you know, we're just looking at 10 bits or something. Just to see what's going on there. Because if we're getting like some random failure in the middle, then that indicates it probably isn't software and that there's something else weird going on. Like maybe there's some sort of a bug in the queue management logic and somehow that the active bit is getting read incorrectly. I mean, I'm not sure exactly how that could happen. Maybe it's some sort of a RAM inference issue, perhaps. I don't know.
Yeah. This the point is what we did today is remove patches we applied to the queue manager to circumvent timing issues on the Intel device, and we had one patch there. I'm not really sure if it's one of these patches which are part of the public merge request. I'm currently not sure, but we removed that patch, which is was a non-trivial change to the queue manager, but unfortunately it didn't change anything. So of course we thought, well, we broke it with that patch, but apparently it's not the case.
As they say,
so,
the plot thickens.
I wouldn't say so. We're also moving in from the other side, taking a pure upstream design, and we have added counters, our counters at the interface level there, especially counting the errors. And from this experiment, we don't see any errors there using the upstream design for the ZCU, I have to add. For the ZCU 106, applying the same test to it.
So whatever's going on, it seems like it's probably specific to the to Intel devices somehow.
Or our changes, which are not that huge, but
but could you
can't rule out at this
but could
point.
you take those changes and run that on the Zinc device? Or have you tried that?
Yeah, that's a third path we are following, kind of including our changes and doing a SetsU build. And unfortunately, it is kind of a third effect there. We also see errors there, but not the effect on the bandwidth is not there. It's still reaching 9.4 gigabit or something like that, a little bit below that.
Okay, so that's interesting. So you're seeing a
yeah,
similar number of errors. You're still seeing that error bit toggling, but somehow it's resulting in less disruption.
yeah. This, I mean, to get the complete picture, we have to add one specific change we made so far is reducing the frequency and doubling the reducing the PCI Express AXI frequency and doubling the Ethernet data path to make the SetsU design more similar to what we are currently using on our custom board due to timing problems with Gen 3. We had to are still at Gen 2 there with our custom board. And with Gen 2 on our custom board, we are using just 125 megahertz. I guess we already discussed that. And that's one particular change we did to the SetsU design itself, kind of to get similar to our custom board, at least while we are still working on getting timing for Gen 3. So the thinking there is also the whole picture has something to do with this reduction of frequency, perhaps, or might have to do. So I'm currently not sure if we are looking at one problem or two problems. Might as well be two problems. So I guess a question would also be, I think my colleague Andreas told me that you told him that you're basically always only testing with Gen 3, since, well, that's what is wanted in general, and that the Gen 2 kind of support, if we call it that way, there might be an issue, so to say.
I mean, I have not been testing with Gen 2 because I figure you can just drop it to whatever previous gen you want and it'll just work. Because I'm not sure what would really introduce any issues. You know, the interface is the same, it's just running at a different frequency. So raising the clock frequency could be a problem, potentially, you know, if it doesn't close timing, but lowering the clock frequency for the most part should just work, right? So, but maybe that's not the case. If I need to run a test at Gen 2 on a particular board, I can certainly try that. I know you guys had asked about potentially doing a test with the MX board that I have here, the Intel board. So I haven't had a chance to do that yet. But I can certainly try that, and then I'll see if there's a board that I can drop down to Gen 2 easily. Man, maybe also the the MX board, and just see if that does anything. I gotta check on that. The Intel the Intel IP cores seem less configurable than the Xilinx ones. Xilinx ones you can just pick, you know, they have their upper limit in terms of what they can do, and you can just pick whatever configuration you want, and you know, it'll implement that. With the Intel boards, like I think with the Gen 4 capable stuff, you can't even select Gen 2 speeds. It's like Gen 3 or Gen 4, and you can do, you know, full width or bifurcated 2 ways or 4 ways.
Yeah,
and that's it.
Perhaps if we go that route, then perhaps Uli, we could provide our our patch for our board to make it Gen 2, which kind of should apply to the Stratix 10 one, I guess.
Right, yeah.
Yeah, but
Yeah, I mean,
I guess for Stratix 10, it's pretty straightforward. We just changed the setting of the IP core.
Yeah, I
So
think
that
that's
was-
all you need to do. So I could certainly try that. I mean, the other thing is I've been doing all my testing. Well, actually, I guess I don't have those boards running at by 16 yet for timing closure reasons. I think it's still running by 8. I'll double check on that though. Are you running by 8 on yours?
Yeah.
Okay.
So perhaps my gut feeling is the more important question would be the doubling of the Ethernet data path. Yeah, direct question. How well is it tested?
I mean, all the 25G designs have the data path doubled, and
Mhm.
those all hit line rate just fine.
Okay.
And I think I've even tested that on the Intel device as well, right? I think the default design for the 520 and MX is
Yeah.
a 25D design with the doubled width.
Okay, because that kind of leads to another problem we have.
Oh boy.
It's always one more, where all of a sudden we detected hardware checksum errors.
Okay, I've
and-
seen messages about that as well, and I tried to do a little bit of snooping, trying to figure out what might have been going on, and even just taking the packet data that was dumped out in those messages and converting it back into a packet I could pull into Wireshark, the packet looked fine. I don't remember about actually checking to see if the hardware checksum reported for that packet made any sense. So
we did
that
that.
was a bit of, yeah, okay.
I did actually capture such a run and correlated it to the message to a certain packet, and at least Wireshark says that the checksum in the packet is okay.
No, so this is in the RX direction. So I suspect the checksum that it's complaining about is the checksum that was returned in the completion record, so not the checksum in the actual packet. Because in the receive direction,
sure.
yeah. So that one is just I guess a ones complement checksum, I think, over every 2 bytes starting at the end of the Ethernet header over the entire packet. So it's possible. So that was something on my to-do list to try to figure out what was going on with, but I'm not sure why I'm only seeing that message for the Intel devices and not for the Xilinx devices. That was a real head scratcher, because I think in the testing that I've done, I've definitely seen it a couple times on a couple different Intel boards, and not just the Stratix 10, but also on the Agilex boards. But I have not seen it at all on the Xilinx ones. So
yeah, we neither. Okay.
it's possible it's related, it's possible it's unrelated, but it is definitely a head scratcher.
Yeah, I guess what we can say is that the problem is worse when doubling the Ethernet data path width.
Interesting.
So it's kind of without doubling, it happens, I don't know, only a handful of times over 30-40 seconds.
And you're seeing this on only the Xilinx devices, or Xilinx and
Intel,
only the Intel devices, or on
only
both
Intel
and
so
Xilinx?
far?
Okay,
Yeah,
only Intel so far. Well, you said you were seeing some errors on the ZCU 106, right?
right. The error bit from the descriptor fetch, that's the other the other bug. So this is, yeah, might have to do something with also our custom board with PCIe. We don't know. The point is, we are seeing these hardware checksum errors happen in the area of kind of a handful over 30 seconds when we are currently not doubling the Ethernet data path width. And when we are doubling it, since we are at Gen 2 and we need to double it to reach 10 gigabit, then the number of hardware checksum errors over roughly 30 seconds rise to 100 or even 150, something like that. So yeah, significantly more hardware checksum errors when the data path width is doubled. That's our currently status with this problem. This problem is currently on hold, but still, I thought I'd ask here if that's kind of a known thing.
Yeah. I've definitely seen that hardware checksum message, but yeah, I have not had the chance to really dive down and try to figure out exactly what was going on, especially because my thoughts on that so far is that not every packet generates that message, right? So whatever is going on, it's sporadic. So it's not like there's a some obvious bug in the data path logic that's resulting in the packets being corrupted, because then you wouldn't send any data, you wouldn't receive any data. And it's also not resulting in all of the checksums being bad, right? Because then, again, you would be getting these messages for every packet. But there seems to be it seems to be generated with very low probability. So what could be doing that is the real question. So the design is close timing, so it's not like a timing violation causing this, I don't think, unless there's something wrong with the timing analysis and it didn't do its job correctly, or the constraints were set up improperly. It's running at a slightly different clock frequency than expected, maybe. But seeing it across many different devices seems to indicate that might not be the case. So if that's not the case, then what else could be going on? I mean, potentially there's some sort of handshaking, back pressure corner case somewhere that's resulting in something getting screwed up, maybe in the descriptors or the completions. Because if the completion doesn't get written out correctly, then it's going to have the wrong timestamp and the wrong timestamp and the wrong checksum in there, and that could trip things up. But I'm not sure why the clock frequency would have anything to do with that, because there's no clock domain crossings in that, right? When you drop down to Gen 2 from Gen 3, you're just basically changing the ratio at the async FIFO for the Ethernet frames that are coming in the door, and that happens long before the packets go through all of the checksum computation stuff and whatnot.
Well, I guess one idea we had was, isn't there a separate data path that actually transports this metadata, like timestamps and the checksum to where the completion is built? So might this be some, I don't know, the head of the FIFO is read twice, or one item is lost, or something like this in the metadata path, and then it doesn't match the actual data anymore?
I mean, I guess it's possible. So I guess one difference between the clock rates is not so much the clock rates, but more the packet rate. So effectively, you're doubling the packet rate. Yeah, so maybe there's some sort of a back pressure issue on one of those. So I guess it's possible. Another thing is that it's not like, or it doesn't seem like you're getting some sort of off by one error, right? So with a back pressure issue, you would expect it to either drop an entry or add an additional entry. and then all of the subsequent packets would be wrong, right? would have the incorrect metadata. So
Yeah.
that potentially makes it easy to debug because you can see, okay, before it happened, everything is fine. After it happened, everything is broken.
Yeah, so we don't know if this actually happens in bursts. Do we know this? No, I think it is not bursts. We should be able to see this as that's a kernel log entry.
Well, I
Yeah,
guess another question about the way that error message is generated, right? Is it like a one-shot thing? It sees that, uh-oh, there's a checksum error, and then it like turns off checksums or something, so it only ever generates it once? Or would you see that multiple times for multiple packets?
yeah.
In
No,
my
it's
testing,
not such a once thing. No, it turns up every time, I would say.
I see.
And it's I mean, I would call it kind of small bursts, but there can only also be single packets where in front of the packet and after the packet everything is okay. So I'd say there are
Interesting.
both cases.
So whatever's going on, it's a pretty localized thing. Yeah, so I noticed this message when testing with like the Agilex devices. So 100 gig link running at full bandwidth, and I would get like, you know, 1 or 2 or something
Mhm.
like that. So it's like super low probability of generating that error. So yeah, it's a head scratcher. Yeah. That is an interesting point about the packet rate being different. I guess I could probably do a once over and see if there's anything screwy going on with those handshaking signals, like forgetting to connect a necessary feedback signal somewhere. I mean, it'd be simple to just to try making any involved FIFOs just bigger, right? Double, quadruple the FIFO size and see if it makes any difference, right?
Yeah.
To make the FIFOs bigger and the bug goes away, okay, then we must have some sort of back pressure issue along that particular path. But at the same time, all of the completion handling stuff, all of that metadata, effectively, none of those FIFOs should overflow because it's only going to be issuing, you know, a limited number of operations along those paths at any given time. So now if they fill up, the ones that are critical, if they fill up, there should be back pressure. So if it's full, then, you know, it won't accept any more packets. And you wouldn't get any kind of an error from that. And I know in a couple cases there are FIFOs that don't have the back pressure signals connected. I think this is more in the transmit direction. But those FIFOs will never overflow because the FIFO will only be able to have like 4 or 5 entries in it at any given time due to how the rest of the logic is set up. And the FIFO is like 32 entries, so it's like it's impossible for it to overflow. Yeah, I guess another thing is just I need to get some of the stuff connected to the statistics collection subsystem so I can just check these counts on all the boards and see if I'm seeing similar behavior anywhere. Because right now I'm basically the only thing I'm looking at is the throughput, right? If it significantly affects the throughput, then it'll be like, okay, there's some sort of a problem here. But like you said, if you're running on the Zinc and you get a few errors, but it's not affecting the throughput, you know, TCP handles the packet drops and, you know, does the right thing. So it's possible we're seeing this on more boards, but it just hasn't been detected until now because for whatever reason, you're getting a much bigger disruption on the Intel boards, which then raises another question. Why do you get such a big disruption on the Intel boards versus the Xilinx ones? And that, I don't have a good feel for why that might be at the moment. That's also kind of unclear.
So just to make sure that you understand me correctly, we are not seeing this on any Xilinx device so far, or I haven't seen it. So it's really only
Well, it is in the checksum problems or
the
error
checksum
bit getting
problem.
set? Okay,
That
yeah,
yeah.
yeah.
The
Okay,
checksum
got it. Yeah.
problem is only on our custom Intel board. And
Well,
the
is
one
that the
thing,
only Intel board that you have? Is the custom board?
more or less, unfortunately, yeah.
Okay. All right. Well, I mean, you said you're only seeing it on your custom board. I'm like, well, have you tried it on a standard dev board, standard Intel board? But
Yeah,
if no,
obvious
then okay.
question.
So we don't know if it's just your custom board or if it's Intel devices in general.
Yeah.
Unless I can repeat it on a different board.
Yeah,
Okay.
that's also why we ask if you could do this test on with a Stratix 10 dev kit. And yeah,
I'll try to get that spun up this week. And you're talking just send some TCP traffic and see if we're seeing those error bits set or.
Yeah, in terms of the hardware, check some, see if these messages turn up or not.
And check for those messages. Yeah.
Okay. Yeah. On the other hand, is bandwidth more or less the question is a 9.4 gigabit really reached? Because the effect of the error bits coming from the descriptor fetcher at our side is, or at our side and for our custom board, is that the bandwidth is dropping down to around 3 gigabits per second instead of staying at 9.4 for the TCP payload rate.
So yeah, I'm trying to think of explanations for why why you would be seeing such a big difference in bandwidth. It's possible that this just has to do kind of with the distribution of which packets get dropped. Because I know TCP can do kind of a fast retransmit where it will basically just retransmit, the one packet that didn't get ACKed. But if you drop too many packets in a row, then it takes a different approach. So what we could be seeing here is just a difference in the number of packets that are getting dropped, right? And the distribution of those. And this is probably why you're not seeing the issue with UDP, because it's probably doing the same thing and dropping packets here and there, but UDP just keeps sending because it has no feedback. But for TCP, it's possible that Xilinx versus Intel, for whatever reason, with the Intel devices, maybe they're getting dropped in batches, right? Like 10 packets in a row get dropped or something like that. And then TCP goes, whoa, what happened? And backs way off. And then more packets get dropped and it backs off more or something. Although that raises another interesting point, is then if TCP is backing off so much, well, now your packet rate is also low. So what and the thing's not under load, right? So why would it be creating more errors due to back pressure or whatever bug we might be seeing here? I guess under short time scales it might be bursting at 10G, so maybe that's not very relevant.
Yeah, so
I guess Joachim, one thing we could do is let's do one of these tests and do a capture alongside with it and see whether we see like a triangular pattern, traffic being ramping up, also bandwidth being ramping up. Then if we see a burst of issues, we will see this with traffic will go down or bandwidth will go down fast, as Alex explained, and then that helps possibly to see which packets are getting retransmitted. So from the sequence numbers, we can tell if it's a burst error or if it's not, because we don't have any additional traffic, right? So it's more or less just these TCP packets that are going through the system. And
Wireshark will highlight all the retransmitted packets as well. There's ways you can filter for those pretty easily. So right. That's another thing to try, I suppose. Yeah,
I just wanted to add that the number of lost packets is not that huge at all. I mean, we are always testing 30 seconds, and it's usually in the range of 500 to 2,500 packets which are lost according to the switch. We are interconnecting the machines over a switch and can easily let the switch count packets which are going in and out. And since we are doing also, among others, a bridging test, this comparing in and out is kind of easy.
So you're bringing up multiple ports on the board. Packets come in one port, they get turned around and sent back out another port.
Yeah, that's also
I
one
see.
of our tests. We're not only doing the point-to-point iPerf thing, we are also doing a bridging test where a separate entity is firing at the MQNIC at one port, and it's configured as a bridge, layer 2 bridge, and should just send out the packet on the second port.
Got it. Okay.
But the effect, and over that bridge, we are doing iPerf with TCP. But the effect is kind of the same, no matter if we do this bridging test or the more peer-to-peer, the easier test, having two machines talking to each other and doing iPerf TCP. The effect of the bandwidth reduction is the same, I would say. If in detail the effect is different but causes the bandwidth to be reduced, that's another question. So with the bridging test, that was actually the second test case we added. I simply wanted to move the TCP processing itself, the iPerf, and the stack away from the machine which drives the MQNIC part. And
just kind of for isolation purposes, just to see what it does to performance. Yeah, okay.
Yeah. And the strange thing is we are also doing UDP over that bridge. And for UDP, we simply cannot reproduce this effect. Obviously, UDP in this case is fire and forget.
Wait, so when you're doing the bridge test, are you still seeing packet drops with UDP?
Yeah, of course there are packet drops since it's simply a fire and forget and
right. No, okay. So you're still seeing some packet drops. You're seeing packet drops for both TCP and UDP. Only TCP has the significant bandwidth reduction, because TCP actually reacts to things. So yeah, okay.
And UDP, it reaches in both directions. I mean, two ports are involved here. It reaches the 9.8 gigabit.
9.8.
9. Sorry. Yeah.
What's your
I don't know.
size?
I don't know the payload. I don't know the payload rate.
Okay. Yeah, cool.
I always have the
different
MTU
numbers.
rate.
Yes. I'm so used to using iPerf that always reports 9.4. Yeah. Okay. So 9.8. So that's so that's also not quite 10G. Oh, but what's the MTU size or the packet size that you're sending?
No, it's exactly what is expected with UDP. So we are using MTU 1500, so the default one, and so we are using a payload for UDP which is 1472 is the maximum for this MTU, and then the I'll call it the layer 2 rate without FCS is 9.84 something, and that's I would say that's what's expected. Yeah, we are not using iPerf for UDP in this case.
So many different ways of measuring the rate, and you can get different numbers depending on exactly what you're measuring.
Yeah,
that makes sense.
In this case, we are measuring using the Linux packet and byte counters.
Got it. Okay. Well, I thought you might have been measuring on your switch or something.
We are also measuring there. We are measuring at multiple points.
Makes sense. Okay.
So I mean, this is might be another aspect which, from my point of view, kind of points to the PCI Express IP core interconnection with MQNIC. Because
Okay.
why, for some reason, the TCP protocol might be affected by this, interconnection from MQNIC to PCI Express. Because why is this not the case for UDP, even in both directions, when packets are going in both directions?
But issue, what do you define issue? What of all the potential bugs that we've been discussing here, which one are you talking about specifically?
The bandwidth reduction case, not the hardware checksum problem.
Well, I mean, the bandwidth reduction in TCP is due to the TCP control algorithm responding to the drop packets, right? So UDP, it doesn't care, it just sends. So even if you get some drop packets, you're still going to run it at approximately the full rate. Or you're just going to keep sending as if nothing happened.
Yeah. So to perhaps put in other words, the issue we are having is, for some reason, unfortunately, hitting the TCP protocol in such a bad way that bandwidth is reduced.
Right. Yeah. That's what I was scratching my head over as well. It's like, you said you're seeing some of these error bits set on the Zinc devices, but it doesn't seem to affect the throughput.
Yeah, that's another
devices,
thing.
You do have a significant drop. So I guess there's two possibilities, right? One possibility is that it's something to do with, the PCI Express interface, because that's different between the two FPGAs. The other possibility is that, maybe there's some difference in the distribution of exactly which packets are being dropped, right? And on the Xilinx devices, the distribution is such that the TCP fast retransmits are just taking care of it, and it's not switching into what the AIMD or whatever to back off a significant fraction. Versus on the Intel devices, maybe it's dropping packets in pairs or something like that instead of individual packets. And then that really causes TCP to get screwed up. Now, why there's that difference, I'm not sure. I guess it's possible it could be related to PCI Express, but not so much in that the interface formats are different, but perhaps in the timing somehow. I think so. I know one thing about Xilinx devices is they have a completion buffer, so it won't send out a read request unless there is space for the corresponding completions in the buffer. So that means that you can only have, like, I think 32 kilobytes worth of reads out active at any given time. The Intel devices don't do that. So if you send a read, it'll just go out on the wire immediately. And you can have as much read data pending as you want. It's then up to your user logic to make sure that you actually accept all of those completions in a timely manner, so things don't get backed up into the host. So I'm not sure if potentially some performance difference with associated with the PCIe IP cores is having an impact here. It's possible. I'm also not sure exactly how you would test for that. You can't really take the Intel PCIe IP core and drop it on a Xilinx device. So or vice versa. Although I guess with their tiles, maybe you could add it.
It's all software.
I'm also wondering, have you tried on any other host computers? Or have you always put the cards in the same machine? I'm not sure if it would have any impact on anything, but
yeah, we have two different host machines, an older one, a newer one. And the effect, as far as our custom board is concerned, are more or less the same within measurement stuff, I would say. our Xilinx board, the ZCU board, is currently sitting always in the same machine.
Right. Okay. I guess you have your whatever it was, tools for scripting access to that, presumably. The lab management.
Yeah.
things.
We're
Yeah.
heavily using that there. Yes. Yeah. Okay. I would say good discussion.
I have a few things to look into, I think. Yeah. Okay.
Yeah, and we will definitely have to look at the Wireshark dump, even if it gets quite big. Should be doable to perhaps detect a scheme, how packets are dropped.
Yeah, I know what I've done a few times is packet captures from both ends of the link. And then if there's a particular packet that gets screwed up on one end, you can go find it in the dump on the other end and figure out what happened. I've definitely debugged a few bugs that way.
Yeah.
When something weird
I've
happened.
done
And-
it via our switch, which has a mirroring possibility. So all packets are sent from the switch to a third host, which is then also not doing anything else.
Right. Well, yeah. Okay. So I guess if
capturing.
you're doing this turnaround stuff, that could work. Yeah, there was a data corruption bug quite some time ago in Corundum, where certain, under certain conditions, the transmit packets would get screwed up, and yeah, I figured out what was going on there by capturing from both ends of the link. The data before it was sent to Corundum, the data after it was received on the other end, found the retransmitted
Yeah.
packet, went back, found the original packet, copied out the hex, pasted it in text files, did a diff, and I'm like, oh,
Yeah.
that's not good.
Yeah.
Figured out what was going on pretty quickly, but it took a while to rewrite the DMA engine to fix the problem. But
Yeah.
yeah. All right. Well, I guess at some point I'll take a look at the design on the Stratix 10 MX board, and I will try both at Gen 2 and then also just with the stock design and see what things look like. Yeah, hopefully we can get this rooted out. It's very strange that it's affecting the Intel boards more than the Xilinx ones. So yeah, that's definitely a real head scratcher, because I've never seen the checksum failure message on the Xilinx boards with all the testing that I've done, but I've definitely seen it several times on the Intel ones. So so I guess another possibility is there could be that there is a bug on the Xilinx ones. The bug affects both, but it's just with such a low probability on the Xilinx ones.
Yeah.
I haven't seen it. So, well, hopefully we can root it out.
Yeah, so my thought was that it could have to do something with how in the end data is routed to the hard IP, because isn't it the case that the Intel one has just 2 interfaces instead of the Xilinx one that has 4 interfaces, so the Axis Stream interfaces?
Right. Yeah. So
and
it has to be
somehow,
merged. Yeah.
so this adds some depending on the traffic patterns, obviously, that might add some additional corner cases with back pressure on these interfaces on the Intel side.
I mean, the Xilinx devices are going to have to merge it internally anyway. So,
yeah, but that's not
I guess it is
Corundum
possible
code, right?
that there will be. Right. Yeah. But the thing is, there's kind of several levels removed from the PCI Express interface, right? So the PCI Express hard IP core is connected to the shim. The shim has a bunch of FIFOs in it. That's then connected to the PCI Express DMA engine, which is handling the PCI Express traffic directly. Then the only connection from the DMA engine to the transmit receive engines and the descriptor handling logic is through the just the DMA descriptors, right? Not the actual traffic, because that just goes into dual port RAMs. So I guess you could see a difference in terms of how quickly those things are being accepted for read or for write by the DMA engine, but I don't know. I mean, it seems a little far-fetched that a problem in the DMA engine or a difference in the interface at the hard IP core level would affect the deep core logic that's quite separated from PCIe in this very specific way, without causing all sorts of other weird problems, right? I mean, like you could be expecting data corruption or things being written to the wrong locations, or incorrect indices in the completions, or things like that would definitely indicate some sort of problem there. But for the most part, that seems to be working as expected. But I mean, yeah, that is a difference between the two. So it's possible that that we're seeing some minor difference in the performance that could be having some deeper effect. I'm not sure. I mean, it's like I don't think we're seeing any kind of anything on that interface that's causing the data corruption. It's I think the only thing we could be seeing is some sort of a timing related issue. I'm not sure. Definitely going to require some more poking around to see if we can get a handle on what's going on here. I am going to take a look at all of the metadata paths as well, just to see if there's anything that looks weird. But well, I think we'll just have to take this one step at a time, run these experiments with the StratX10 MX board, and then see what things look like from there. Does that sound good to you guys?
Yeah.
Maybe.
Mhm.
Okay. All right. Was there anything else that people want to discuss today, or will we call it a successful meeting and reconvene in 2 weeks and/or on Zulip?
Sounds good. Thanks to all of you.
All right, sounds good. Thanks to everybody for tuning in today,
Thank you.
and have a nice couple weeks. We'll see you on what, the 14th, I think. 14th. I can do math today. The 24th.
24th, yes. I think you had heart attack. Oh no, you just woke up, right? I forgot.
All right. Well,
Sounds good. Thanks a lot, Alex.
sounds good.
Thank
Bye.
you. Thanks, everyone.
All right. Well, talk to you guys later.
Stay safe and be careful.
Yeah, you especially.
Yes.
All right. Talk to you.
Thank you.